start now. Is this on? I think it's on. Okay, good. Okay, so yeah, so what I want to do today is I just want to explain why SLE is the right process to describe the flow lines of the Gaussian free field. So when we constructed the flow lines of the Gaussian free field, I gave you kind of a heuristic explanation that told you that SLE had to be the right thing. And now what I want to do is make this a bit more mathematically precise. So before I do that, let me go back and just remind you of the theorem statement due to Sheffield that gives you the form of the SLE Gaussian free field coupling. So again, the statement is that you fix kappa between 0 and 4, and you have this constant chi, which is 2 over square root kappa minus the square root of kappa over 2, and another constant lambda, which is pi over square root of kappa. And you assume that you have a Gaussian free field, h on the upper half plane, and then I called calligraphic h sub 0. This is the function which is harmonic on the upper half plane, and the boundary conditions are given by minus lambda on the negative reals and positive lambda on the positive reals. Okay. And then you suppose that you have an SLE. So eta is going to be an SLE kappa process, which is independent of h. Independent of your Gaussian free field. And I'm going to let g sub t, this is going to be its Loevner driving function. Oh, sorry, associated Loevner flow. So remember, this just means this solves the Korda-Loevner equation. Where w is its driving function, and I let f sub t be the centered Loevner flow. So it's just what you get when you take g sub t and you subtract from it w of t. And then the last object in the theorem statement is the calligraphic h sub t, and this was given by calligraphic h sub 0 composed with f sub t minus chi times the argument of ft prime. And then the theorem statement is that if tau is any eta stopping time, then it's true that h plus calligraphic h sub 0 is equal in distribution to h composed with f tau plus h tau. Okay, so this was the theorem statement, and we did kind of most of the proof of this 2 times ago. And let me just remind you that the idea for how to prove this is that number 1, you sample your SLE kappa. And then once you've sampled your SLE, you sample your Gaussian free field in the complement of the path. And you show that when you integrate over the randomness of the path, you get a Gaussian free field on the entire upper half plane. Okay, and so what we did is we did most of the proof that shows that if you sample your curve as an SLE process, and then you perform this procedure, then you actually get a Gaussian free field on the upper half plane. And because of the sort of interpretation of this function h sub tau here, which gives you the boundary values of the Gaussian free field along the path, we interpreted this as constructing a flow line of the Gaussian free field. But one question that you could ask is whether or not the law on SLE curves is the only law on paths that makes this work. And what I'm going to do now is I'm going to explain or prove mathematically that SLEs are the only ones that make this construction actually work. So this is the question we want to answer. So is SLE kappa the only law on say simple paths that makes this construction work? And the answer to this question is yes, and now I'm going to give the proof of this. And one thing that I want to emphasize is that this is the proof of this fact, actually a slightly more general version of this, is really important in the theory because this is what allows you to compute the conditional law of one path given another when you consider multiple flow lines. So this is an important idea in this whole theory. Okay, so what I'm going to do now is I'm going to suppose that that I have some other simple curve. So this is any simple curve in the upper half plane, which goes from 0 to infinity. And I'm going to assume that this path is coupled with a Gaussian free field. H on the upper half plane, such that for any eta stopping time tau, we have that the analog of the theorem statement holds, but with this path in place of what we assume to be SLE. So we have that H plus H0 is equal in distribution to H tilde composed with F tau plus, say, H tilde tau, where here Ft is the centered Loeffner flow for my path eta, and H tilde is defined analogously to this calligraphic H tilde is defined analogously to the previous calligraphic H, but with this path in the place of the SLE. So, and H tilde sub t, this is just going to be equal to H0 composed with Ft minus chi times the argument of Ft prime. Okay, and here H tilde, this is a Gaussian free field on the upper half plane independent of eta. Okay. All right. So what this says, what we're assuming here. Oh, sorry. Yeah.
Outside of your equation, which H is that? Is that the original H?
Oh, this is the H. So we think of eta as being, say, coupled with a Gaussian free field, and so in the language of the theorem statement, this would be kind of like. So where did it go? Right. So this would be kind of like what you would get over here on the right-hand side if you took tau to be infinity. Okay, so what this says is that this eta up to time tau, this is a local set for the Gaussian free field, so for H, and it has these sort of flow line boundary conditions along the trajectory when you condition on it. And well, what does the fact that this is local tell you? Well, it tells you that if you let f sub t be the filtration generated by the realization of the path, then what you get is that the conditional expectation of your Gaussian free field at a point z, given f sub t, this evolves as a, this is a martingale in t. Okay. So you know that for any fixed z, if you calculate the conditional expectation of your Gaussian free field at time t, then this is going to be a martingale. Now, of course, this requires a little bit of interpretation here because I'm taking the conditional expectation of a distribution at a point, and of course, h doesn't have values at points. But the way that you think of this is that this would be the same thing as what we defined before, this calligraphic C associated with the local set given by eta up to time t. And what we're going to do now is we're going to extract from the fact that this is a martingale, which for a given time t, if you let z vary, is a harmonic function with these boundary conditions. So the boundary conditions that come from this h sub tau, we're going to extract from this that eta actually has to be SLE. And the idea to prove this, this is taken from a work of Julian Dubada. So this is based on the presentation in Julian Dubada's his article SLE in the free field. Okay. All right, so here's the idea for the proof. The first thing that we're going to do is we're going to let say h hat of t. This is going to be the harmonic conjugate of h tilde of t. Okay, and if I take the harmonic conjugate of h tilde of t and I add them together, then their sum, so h tilde of t plus I times h hat of t, this is an analytic function. And the reason I'm adding the harmonic conjugate to h tilde is that in the definition of h tilde there are some arguments, and it's going to be convenient in just a moment to have log functions rather than arguments. Okay, so now let's just write out explicitly what this function ht star is. So since the harmonic conjugate of the argument function is just is the log function. Actually, sorry, I'm going to be multiplying h tilde by I. Actually, so, okay, but I still get an analytic function. Anyway, since the harmonic conjugate of the argument function is just the log function, the log of the modulus, we can write down what ht star is explicitly. So let's first write down what ht tilde is. So ht tilde, this is equal to the composition of h0 with ft minus chi times the argument of ft prime. And this, if you think about it for a moment, you'll see that this is the same thing as lambda minus 2 lambda over pi times the argument of ft of z minus chi times the argument of ft prime. Okay. And the reason that this is the right explicit form of this function is that if you pretend that t is equal to 0 here, you just put in the function z, then the function that I've written down, this first part here, this is the function which along the real axis, where the argument is equal to 0, will just be lambda, and along the negative part of the real axis, where the argument is equal to pi, you're going to get minus lambda. Okay? So this is exactly the same. This is exactly the same as this function up here. All right, and now if I add to this its harmonic conjugate, we get that ht star. This is going to be the same thing, except for I'm going to replace all of the argument functions with log functions. So this is lambda minus 2 lambda over pi times the log of ft of z minus chi times the log of ft prime of z. Okay, so this is very nice now because now we have an explicit formula for what this ht actually is. No, so star is what you get when you add. Okay, so the harmonic conjugate of the argument function is the log with log of the modulus here, and this is the right. This is just the usual log. Okay. All right, so now let's use this. So first of all, what do we know? Well, we know that this ht star of z, this is going to be a martingale in T for each z fixed. And the reason for this is that, well, we know that ht tilde, this one up here, this is a martingale in z when t varies. And the harmonic conjugate, ht hat, this can be just represented as a linear, this can be gotten from ht tilde in a linear way. And so since a sort of linear transformation of martingales is going to give you a martingale, it follows that this guy here is also a martingale. And what we want to do now is we want to get from this that first get that the Loevner driving function for our path eta is a semi-martingale. So I'm going to let w of t, this is going to be the Loevner driving function. For eta, and as before, I'm going to let g sub t is going to be just the regular Loevner flow for eta. So here, ft and gt are related in the usual way. So ft is equal to gt minus wt. Okay. And now what I can do is I can take my equation here, ht star, and let me just rewrite it in a slightly different way. So this is the same thing as saying that ht star of z is equal to lambda minus 2 lambda over pi times the log of gt of z minus w of t minus chi times the argument of ft prime. Okay, so now we have this, this equation here, and what do we know? So we know that this here, this is a continuous local martingale. Okay, so that's good. Also, this gt here, remember gt just solves the Lovener equation. Okay, and so since this solves a nice differential equation, gt is a process of bounded variation. And since it has bounded variation, it follows that gt of z, this is also a nice semi-martingale. So this is a good term. And similarly, because ft solves the SDE, dft is equal to 2 over ft of z dt minus dwt. Because remember, this is just given by the centered Lovener flow. It follows that if you take a derivative with respect to z, you get that dft prime of z is equal to minus 2 ft prime of z minus 2 ft prime of z divided by ft squared of z dt. Okay, so the dwt term just cancels because it doesn't depend on z. And so, this is another process of bounded variation, and so ft prime of z is also a nice semi-martingale. Okay, and so we have this equation now where we have a martingale is equal to a nice function of a semi-martingale minus w minus another semi-martingale, and therefore you can solve for wt, and it's just going to be a nice function of semi-martingales of continuous semi-martingales, and therefore w of t is a continuous semi-martingale. Okay, so that's the first part of the proof. And now we want to identify what it is exactly. So since it's a continuous semi-martingale, we know that we can write w of t as a sum of vt plus mt, where here vt has bounded variation and mt, this is a continuous local martingale. Okay, and what we want to do in order to finish the proof, remember we want to show that this is the driving function for an SLE kappa process, so we want to show that this vt term has to be 0 and mt is just given by square root kappa times a Brownian motion. And once we do that, we'll have our uniqueness result for SLE. And this is just going to follow from one more little calculation. All right, so so what we want to do now is we want to show that vt is equal to 0 and mt is equal to square root kappa times bt, where b is a standard Brownian motion. All right, so now we have to do a little bit of calculation to figure this out. So we already, well, first let me write down what the derivative of the various terms are that appear in the definition of ht star. So this we know. So the time derivative of just the log of ft prime, this is given by 1 over ft prime times 2 over ft of z prime. And this is the same thing as minus 2 over ft squared of z. Okay, so this is the derivative of this gives us the derivative of the last term here in ht star. Now let's calculate the derivative of the first term. So the d log of ft of z, so this is going to be equal to 1 over ft of z, and then you have the ft of z minus 1 over 2 ft squared of z, and then you have the quadratic variation term, quadratic variation of ft of z. Okay, and yeah, and so let's just expand this. So this is equal to 1 over ft of z, and then you have right. So you have 1 over ft of z, and then you have dft of z, and this is 2 over ft of z dt minus dwt. That's the first term. And for the second term, we have minus 1 over 2 ft squared of z. And remember, ft of z is just equal to gt of z minus wt. And yeah, so this term here, the gt, this is just a process of bounded variation, so it's not going to contribute to the quadratic variation. And in w, the only part that's going to contribute to the quadratic variation is the martingale part. And so what we're going to see here is just the quadratic variation of m sub t. Okay. Right, and this, let me expand it one more time. This is the same thing as 2 over ft squared of z dt. And then we have minus 1 over ft of z dvt from the bounded variation part of w, minus 1 over ft of z dmt minus 1 over 2 ft squared of z, then the quadratic variation of m sub t. All right, so now we can combine the two calculations that we did. So the derivative of log of ft prime and log of ft to write down the derivative for ht star. Okay. Now, remember, what we want to do here is we want to get a handle on the we want to show that vt here is equal to 0, and we also want to show that the quadratic variation of m sub t is just given by kappa sub t. Okay? And the way that we're going to do that is we're going to use that since this ht star of z is a martingale, is a continuous local martingale, So its drift has to be equal to 0. And what is its drift equal to? What is the drift term? So the drift term is just going to be minus 2 over lambda, minus 2 lambda over pi times the drift term for the log. So that's this thing here. So you get 2 over ft of z squared dt minus 1 over ft of z dvt minus 1 over 2 ft squared dmt. And then the other part of the drift term is just coming from the log of ft prime. So this gives you minus chi times minus 2 over ft squared of z dt. And all of this has to be equal to 0. Okay, and now, so the idea here is that if you look at the formula for this drift term, you see that there are 2 types of terms there. There are the terms which involve ft squared. So this term, and this term all have an ft squared. And then there's this term with dvt, which is the lone one where you only see an ft. So there's no square there. Okay, so what this means is that you can pick. There are kind of 2 different ways to do this. So one way to do it is that you can pick 2 different z's, or by evaluating, say, this expression at distinct points, say z and w, in the upper half plane, minus the curve. What you can see is that if you evaluate this expression at 2 different points, then you can pick out the terms which have the ft squared in front of them and the term which has just the ft in front of it. And just by solving, so you have by solving that the vt term just has to be equal to 0. Okay, because you get 2 equations, and you can just solve for the one which has vt, and you get that vt is equal to 0. And you also get that all of the terms which have the ft squared in front of them have to be 0 too. So you have minus 2 lambda over pi times 2 minus, let me keep the dt, minus 2 dt minus 1/2 dmt plus 2 chi dt. Okay, and this all has to be equal to 0 too. And let's just multiply this out and figure out what this tells us about the quadratic variation of mt. So this tells us that minus 4 lambda over pi plus lambda over pi. Sorry, let me keep the dt's. So times dmt plus 2 chi is equal to 0. And now we're just going to solve for the quadratic variation of mt. And so what do we get? So we get lambda over pi dmt is equal to 4 lambda over pi minus 2 chi dt, just by rearranging the two sides. And if we multiply both sides by pi over lambda, we get that dmt is equal to, let's see here, so you get 4 minus 2 chi pi over lambda dt. Okay, and now to finish, let's just calculate what this is actually equal to. So let's do it in this little box over here. So let me remind you over here that chi is equal to 2 over square root kappa minus square root kappa over 2, and lambda is equal to pi over square root kappa. Okay, so if we just insert these formulas into this expression, we get that 4 minus 2 chi pi over lambda is equal to 4 minus 2 times 2 over the square root of kappa minus square root kappa over 2 divided by lambda times pi, and of course the definition of lambda is just pi over the square root of kappa. All right, and the pi's cancel, so that cancels with that. And if I multiply through the square root of kappa, I get 4 minus 4 plus kappa. So in the end, I get my kappa in the end. And that finishes the proof, because this tells us that the quadratic variation of m is just given by kappa times t, and the only continuous local martingale that has that quadratic variation is square root kappa times a Brownian motion. Okay. So that's it. And so this tells you that there's only one process that you can couple with the Gaussian free field, so that it's a flow line in the sense that I defined before. And as I mentioned earlier, this result is very important in the theory because it's also what allows you to calculate the conditional law of one path given another when you try to couple many SLEs with the Gaussian free field.
Jason, I mean, this depends a lot on your choice of chi and gamma.
Right.
I mean, is the result still hold if you have more flexibility there?
Sorry?
Does a similar result still hold if you relax that?
In what sense?
So I mean, you're okay. Lambda's fine. You've got to make some kind of choice. But with chi, I mean, if you chose a different chi, could you get different processes?
Yeah. So with each value of chi, you're always matched with exactly one value of kappa. So chi and kappa determine each other.
But if you don't do that, can you get a different process?
Oh, then it's not going to work. Yeah, you can't get that to work. So what will happen is that, yeah, I mean, you won't actually be able to construct a coupling with the Gaussian free field if you don't match chi and kappa appropriately. Yeah, the whole thing will kind of fall apart actually. Does anybody have any other questions about? All right, so now I just want to switch gears in the last 15 minutes or so and show you some slides. Because oops, okay. Yeah, so we've been doing, a lot of the more technical aspects of this theory, so SLE and the Gaussian free field. But because this is a two-dimensional subject, there are also a lot of very interesting pictures that you can look at. And so I thought I would end with something a little bit lighter, more in this direction. I think this is also helpful for getting a sense of what's going on. yeah, so this is what just what the discrete Gaussian free field looks like if you haven't seen this before. This is on a 20 by 20 lattice. And when you take the lattice size and you start to increase it, you get something which starts to fluctuate more and more wildly. So this is what the Gaussian free field looks like on a 100 by 100 lattice. And as you make the lattice spacing larger and larger, you somehow get this more rapidly fluctuating field, and these peaks eventually go off to plus and minus infinity. So I want to explain pictorially now a bit more this first result, which related the SLE in the Gaussian free field due to Schramm and Sheffield. And this picture is taken from their paper. And what it shows you is a discrete Gaussian free field on the square. And it's a little bit hard to see, but what they've done is they've prescribed boundary values along one side, which are all negative. And on the other side, they've prescribed boundary values for the discrete Gaussian free field so that they're all positive. And the reason for this particular choice is, as Vincent explained in his first lecture, is that then this forces kind of a unique interface which separates negative heights of the Gaussian free field from positive heights and connects this bottom corner up here to this top corner. And it's a little bit hard to see, but if you just kind of follow along here, you can see that there actually is this, this black curve here. And what they show is that when you send the lattice spacing to 0, that this actually converges to an SLE4. And kind of the main thing in the input is their discovery of this height gap that I was trying to, I told you a little bit about before. And so what this picture is showing you is what happens in the same setup. So it's this same Gaussian free field. And what they've done is they have computed the conditional expectation of the height of the Gaussian free field given the realization of the interface along with the values of the field along the interface. And what you see is that, although along the interface itself, the field is very, very spiky, you have lots of high and low peaks, what happens is that as you move away from the interface, very, very quickly the conditional expectation just averages out, and you see this, this sort of ridge. Okay? And because the conditional expectation actually averages out to a constant, just a fixed constant on each side, there's this sort of idea that, even though the Gaussian free field doesn't have level sets in the traditional sense, you can still make sense of these level sets. And what they really look like is you have these sort of ridges like this. And in the flow line story, kind of the same thing happens, except for instead of having a height gap like this, what you have is sort of an angle gap. And what that means is that, again, if you could draw this vector field, which is supposed to correspond to e to the IH, then sort of what's happening to the right of the curve is you have arrows pointing inward, and in the left of the curve you also have arrows kind of pointing inward, rather than exactly parallel to your flow line. So this is sort of a very interesting, interesting phenomenon that happens in this theory. And I also want to show you some pictures of what Gaussian free field flow lines actually look like to give you a sense of how they behave. So here, what I've done is I've taken the Gaussian free field, discrete Gaussian free field, and I've actually simulated rays of e to the IH divided by chi, and I've chosen my constant chi here to be about 32. And the value of kappa that corresponds to this value of chi is exactly 1 over 256. Okay? And these curves here that you see, these are all flow lines of this vector field starting from the bottom, from this point here, and they're aimed at the top. And I chose my boundary data for this free field so that the north-going flow line, the one which is kind of going straight up the middle, actually is an SLE 1 over 256 curve. And the flow lines which have a positive angle or a negative angle, these are variants of these SLE 1 over 256 curves. And kind of interesting things start to happen when you decrease the value of chi. So here's what it looks like when chi is about 11. And so these family of curves that you see here are SLE 1 over 32 curves. And things get more and more erratic when you start to decrease chi. So this is what it looks like when chi is about 8. And so these are SLE 1 over 16s. This is chi 3.75. So these are SLE 1/4 processes, etc. And in each one of these pictures, what I'm doing is I'm actually generating a whole continuum of flow lines. So these are flow lines with a continuum of angles between minus pi over 2 and pi over 2. And what you see when you look at these pictures is that, in some ways, these curves behave much like, flow lines would for a regular vector field defined by a regular continuous function because, for example, they respect monotonicity. When you increase the angle from minus pi over 2 to pi over 2, they really do move from the right over to the left. But in other ways, they behave very differently from how the flow lines of a regular continuous vector field behave. For example, if you look here in this region, you see this green curve, and they look like they're actually touching and hitting and bouncing off of the yellow curves. And this is something which is not allowed in the case of a regular continuous vector field because these paths have different angles. And paths with different angles in a regular vector field cannot repeatedly touch each other and bounce off of each other like this. And the other thing that you see when you look at these pictures is that there are these really big holes. There are these huge regions here which are just not being hit by any of the flow lines starting from this point here. And and it turns out that in reality, the set of points that you can actually hit by a Gaussian free field flow line, even if you're allowed to fire them at the whole spectrum of possible angles, is very, very small. So in some of the work that I've done on this, one of the first things that we showed is that the Lebesgue measure of this set is actually equal to 0. So this is a very small set. And we have there's another paper that was written a long time ago but hasn't been posted yet that calculates the Hausdorff dimension of this set. And what it says is that even though this set that you see here consists of many, many SLE 1/2 paths, the Hausdorff dimension of the entire set is actually equal to that of a single SLE 1/2 path. So it's kind of strange if you think about it because, this looks like this should be much, much bigger than an SLE 1/2 because there's a huge number of them here, and somehow you would expect that you might get accumulation points. But in reality, you don't, and this set that you see is actually quite small. And this was very surprising because, if you start to go backwards and I start increasing chi again, you see a family of sets that look like they're getting bigger and bigger. And, if you took a Hausdorff limit with respect to the Hausdorff topology of these sets, you're converging to something which actually has dimension 2 because it's going to be this entire sort of shape that you see here, completely filled in. But the Hausdorff dimensions of the sets that you see are actually converging to 1 because that's the dimension of an SLE 0 curve. So you see this all sorts of kind of strange behavior like that. And what happens when you decrease chi further and further is the picture becomes more and more fractal. And of course, the reason for this is that we're looking at rays of e to the I h over chi. And when you divide by a smaller and smaller constant chi here, you're allowing the Gaussian free field to fluctuate more and more wildly. And those more and more wild fluctuations lead to wilder and wilder flow lines. And when chi goes to 0, what that corresponds to is kappa converging to 4. And what you see is that this entire sort of spectrum of rays will actually just collapse in the chi to 0 limit, and you'll see a single SLE 4 curve connecting these 2 points in this domain. And let me point out another kind of interesting thing which happens in this whole theory. So these are Gaussian free field flow lines, and they all have the same angle. All these flow lines have angle pi over 4. And I've started 20 of them from equally spaced points on the bottom of this square. And what you see is that if you follow any two flow lines, then eventually they're going to intersect each other. And once they intersect, they actually merge, and then they travel together all the way up until the top of the domain. And this is, of course, is very, very different because for a regular vector field, flow lines cannot merge like this. And so what you see is that flow lines of a fixed angle actually form a sort of tree. And here's this red tree here is generated in exactly the same way, except for each of these paths has angle minus pi over 4 rather than pi over 4. Here's one more picture kind of in a similar vein that illustrates some of the different phenomenon. So here is the same Gaussian free field where I'm firing a whole spectrum of rays here with angle between minus pi over 4 and pi over 4. And now I've done the same thing, except for starting from this other point here on the bottom. And again, you see these sort of interesting things where if you follow a given color, like this, say, purple here, then kind of what happens is the purple path goes along, and it will cross all of the paths on this side, which have a different color, until it eventually meets its partner. So the flow line starting from down here with the same color, and once the two partners meet, they merge, and then they sort of stay together and travel up until you reach the top of the domain. And okay, and there's a theorem statement that one can show which tells you exactly how these flow lines interact. So it turns out that if you have two flow lines and one starts to the left of the other one, then as long as its angle points to the left, then they really do respect monotonicity. If they have the same angle, then they always merge upon intersecting and they never separate. And if one of them points to the right of the other one, they're going to cross, and after crossing they start to, they can possibly bounce off of each other, but they can never cross back. And using a small generalization of the theorem that I just presented to you today, you can always calculate the conditional law of one path given another, and it's always a certain type of SLE process, which is called SLE kappa rho. Now, right, so you can completely describe all of the interaction of these flow lines. Now, somebody asked 2 times ago, what sort of happens when you look at SLE processes when kappa is bigger than 4 in the Gaussian free field. And so here's a picture of an SLE6 process that I actually made using the Gaussian free field, and I'm going to explain in just a moment how this was generated. And while I explain that, I also want to explain how there's a certain form of what's called SLE duality, which naturally appears in the Gaussian free field. And so what this says is that if you have an SLE6 path like this, then its outer boundary, so what you would get if you just followed, say, the left side of this, is supposed to look like an SLE 16 over 6 path, so an SLE 8/3. And this is something that was predicted a long time ago by this physicist, Bertrand Duplantier, who will actually be here fairly soon. And if you think about this in terms of discrete models, it's also very natural, like for loop array random walk in the uniform spanning tree. And this has been proved now rigorously in a number of different forms. So this was first done by Dapeng Zhan and Julian Dubeda. And what I want to do is I just want to show you how you see this SLE kappa, SLE 16 over kappa interaction inside of the Gaussian free field. So here in this picture, what I'm showing you is 2 Gaussian free field flow lines. They're both starting from the bottom of the square here. One has angle pi over 2, the one on the left, and then the one on the right has an angle is a flow line of angle minus pi over 2. And what you can do is from each one of the points along the red path, you can imagine firing a new flow line of angle minus pi over 2, and at each point along the yellow path, you can fire a new flow line of angle pi over 2. And what you get is a picture that looks something like this. Another way of describing this is that this is the set of points that you can reach when you travel along Gaussian free field flow lines, and you're only allowed to take 2 angles, pi over 2 and minus pi over 2, and you're allowed to change your direction exactly once. So then this is the set of points that you can access using these rules. And then what you can do is you can increase the number of times you're allowed to change your direction. So this is what it looks like if you're allowed to go change your direction 2 times, and 3 times, etc. And what happens is if you allow the number of direction changes to go to infinity, then the set of points that you can access, so this entire kind of orange blob up here, actually will just be an SLE 16 over kappa process. The difference is that here, the flow lines, the SLE kappa flow lines, these are paths which naturally travel from the bottom of the square up to the top, while the SLE 16 over kappa process naturally travels in the opposite direction. It goes from the top down to the bottom. And this is why, one of the reasons why we refer to it as a counterflow line. Anyway, there's this idea that somehow you're building this counterflow line step by step by growing trees of flow lines. And here's one more picture of what this looks like. So this is the same construction, except for rather than the previous one was actually SLE 16 over 3. This is what SLE 128 looks like if you construct it in this way. So again, this is a picture of a single path. It's not crossing. It starts from the top of the domain, and it goes down to the bottom. And the way it moves is it kind of whips back and forth like this. And eventually it gets down to here. And this is of course related to what Vincent called in his course earlier. This is sort of like what the limit would look like if you were to take a limit. Sorry, what the limit would look like if you were to send kappa to infinity. You just see this path that sort of whips back and forth, and eventually reaches its target point. And here's one more picture of what one of these SLE with large kappa values look like, except in this case I've somehow changed things in order to force the process away from the domain boundary. Okay. Yeah, and there's also a theory that one can develop. It's kind of an extension of the theory of flow lines which come from the boundary, where you actually construct flow lines which start from interior points. And so this is a picture of what Gaussian free field flow lines look like if you start from this point here and you allow their angle to range between 0 and 2 pi. And just like in the case where they come from the boundary, you also have this sort of interesting mess of paths. And you can also start collections of flow lines from multiple points. So here we've done the same thing, except for I've started flow lines from this point here and this point here. And just like in the case where they come from the boundary, when they start from an interior point, they also obey the same interaction rules. For example, two paths like these green ones here with the same angle, they eventually merge, and once they merge, they stay together and forever after. All right, so I'm about out of time here, so I think I'll not show you this, and I'll stop. And thanks for your attention. Does anybody have any quick questions? Yeah.
So if you have a collection of SLE kappa for fixed kappa that starts at different initial conditions, can you reconstruct the Gaussian free field?
Yeah, so there are lots of really interesting questions in all of this stuff about what determines what. So like one of the things that I told you, didn't prove to you, is this result first proved by Dubedat that says that if you see the Gaussian free field, then you can see the SLE. And it turns out that the reverse is also true. So for example, whenever you see an SLE like this one, which actually covers all of space, then this will actually determine the Gaussian free field. So if you see the SLE, then you can recover, if you see the Gaussian free field, you can recover the SLE as a deterministic function. And if the SLE is space filling, like this one, then the Gaussian free field will also be a deterministic function of the SLE.
Is that by completing the windings somehow?
Well, essentially the reason is that somehow what you're doing is, this is actually related to one of the facts we did about local sets. So like, let's say you have a domain like this, and let's say you throw down some flow lines. So when you have these flow lines, you know that the conditional expectation of the height of the Gaussian free field, given these flow lines, is going to be the function which is harmonic and has certain boundary values along the flow lines. So you know exactly what the function is. And you also know from the fact we did about local sets what the conditional variance of the Gaussian free field is going to be given this, this local set. And it just depends on the conformal radius of this point inside of this domain. And what you see is that as you throw more and more stuff down, more and more paths, as long as they're somehow converging to something which is dense, the conformal radius of any point is going to go to 0, and so the conditional variance is tending to 0. And that's enough to say that you can recover everything. And if you condition on something which is smaller, like this one, so this is not a space-filling curve because the right side and the left side are also open, what you get is that just the part of the curve where you actually feel space is going to be determined by the Gaussian free field. And these kinds of things are really interesting in this theory because you can kind of prove all sorts of, or ask and answer actually some really interesting questions like, if you see, one question which is kind of related to this is if you see an SLE 16/3 curve like this, but, let's say I just show it to you as a set and not as a curve, and then I ask, can you recover what the trajectory of this curve was, just given the points that it visited? And it turns out that that's not enough information to recover the path. So the path is not a measurable function of its range. But using the Gaussian free field stuff, you can kind of see how much extra information you need to condition on about this curve in order to be able to recover it. And it's all based on the same kind of ideas as this, kind of what determines what. So it's, in this stuff, that's one thing that people are really interested in trying to understand really well. Does anybody have any other quick? So maybe I should. I'm already a little bit over time, so I think I'll stop there.